So today we're going to start the next section, section 4.3, which is use functions involving e. So I want to spend a little time talking about what e is. So there's some history. I linked a video as well by this funny British guy who kind of talks about what e is, and I will go through what he goes through as well a little bit, but he goes a little more in depth. So basically e, the history of mathematics is marked by the discovery of special numbers such as pi and I, which we work with both of those now. But another special number is denoted by the letter e. So the number is called the natural base. So the natural base e, or the Euler number, or Euler number, after its discoverer Leonhard Euler. So I want to do a thought exercise first. So actually, this number e was first noticed by a guy, a Bernoulli brother, I believe. So they were, during the Renaissance, these Italian brothers who were big into these money. They made a lot of money. They were merchants, but they were also mathematicians. So the one noticed, we did, in the last section, we did an interest growth, remember, where we said y equals your initial amount times 1 plus 1 over n, all raised to the n, right? Actually, I think we said this was r. So 1 over r, all raised to the t, sorry. So where r was our rate, t was our time, and p was our initial amount. So I'm going to use the same thought process here. But let's consider that you have $1 and you put it into an account that has 100% interest rate every year. So every year, this bank is going to pay you 100% of whatever's in that account. So if we wrote that as an equation, it would be 1 times 1 plus, our rate is 100%, so really it's just 1 over 1, which is 1, all raised to the 1, right? Because it's only one time per year. So this $1 would double, essentially, right? And so we'd have $2 at the end of the year. So now let's consider you have this dollar and another bank says, okay, I'll give you 50% interest every 6 months. Is that a better deal or not? So really quick, before just plugging it into this equation, I'm going to go through and show you what happens every 6 months. So this first 6 months, you'll have $1. You will have 1 plus, and 50% interest as a fraction would be 1 over 2, right? And then we could say it happens, so we'll then do 1 plus 1 over 2 would be 150, right? Okay, so after the first 6 months, you have $1.50 in your account. Okay, so now if we were to put it back in this equation without that t, it would be that your initial amount is now 150. And so then if you, again, gave yourself 50% interest on that, you would end up with $225. Okay, so that's doing it every 6 months. And again, I didn't plug it into the equation, but I want to show you why that's bigger. So if you did just plug it into the equation, it would be 1, then 1 plus 1 over 2, and then to the second power, right? Because it's happening twice a year. So basically what I'm going to do is I'm just going to make this r and t match, and we're going to look at what happens. So that was this 225. Okay, so actually it was a better deal, even though it was the interest rate was less, compounding it more often made it a better deal. Okay, so now let's do the same thought exercise. What if I gave you 1/12% interest on your dollar, but I gave it to you every month? So again, I'm making r and t match, but you have that initial amount. You have 1 plus 1 over 12, all raised to the 12th power. Well, then it turns out, if I gave you this interest every month, you would end the year with $2.61. So again, it's a better deal. So now let's consider, what if I paid you interest every week? So if I match my r and my t, that would be 1 over 52% interest. So I start with my initial amount, and then 1 plus 1 over 52 raised to the 52. So again, this interest rate is much less, but if we are compounding it every 52 weeks, every week, That's 52 weeks in a year. So you would end the year with $2.69. So again, it's just growing and growing. So that's what this Bernoulli brother noticed. He noticed it was approaching a specific value. And it turns out that E is this value. If you continue to increase how many times you are compounding this interest, even if you decrease your rate, you're going to approach this value. So what this definition is saying is as n approaches infinity. So that means as we get a bigger and bigger n, so I increased my n every time, you approach E. So E is in your calculator, and it's this number that's approximately 2.718281828. So it's an irrational number. It actually continues on after that. Bernoulli noticed this number, but he's not the one who actually defined this number. That was when Euler came in and defined it in years later. So that's what E is. It's a pretty cool number. It has lots of applications, and it's specifically, we're going to talk about this continuous compounding interest. But for today, I actually just want to focus on simplifying these natural base expressions. We've done this before, but now we're going to work with E. You're not going to be putting E in your calculator yet. It is in your calculator, but we're not going to do it yet. I just want to refresh us on some of our rules when we're using these exponents. So remember, if you have x to the a times x to the b, this is where you add your exponents. If you divide your exponents, that's where you're going to subtract the exponents. If you have an exponent raised to an exponent, so if you see parentheses pop up, that's where you're going to multiply the exponents. If you have x to the negative exponent, right, you'd make it a positive exponent and just flip it. And I think that's basically all the rules, right? And so all these rules are the same now. Nothing's changed. We're just going to use these with E now. So let E be a base. You don't have to put it as a number. This could be represented as e to the 2 plus 5 or as e to the 7. Okay, so that's your final answer here. For part B, remember you can split this up. You can think of this as 12 over 3 times e to the 4th over e to the 3rd. So if you simplify that, 12 divided by 3 is 4. And then it'd be e to the 4 minus 3, which is just 4e to the first power, or just 4e. So this is going to be a bit of a review for you. For number 5, or for part C, remember this 2 goes on both of these. Since 5 doesn't have an exponent, it just picks that up. And then this would become e to the negative 3x times 2. Do evaluate if you have just a number raised to a power, you can evaluate that. So 5 to the second power is 25. And then this would be e to the negative 6x. I don't like negative exponents, so remember to get rid of this negative 6x, you would make it 25 over e to the positive 6x. So this is going to be what your homework today looks like, just simplifying these expressions using e. We'll get more into the practical applications of e tomorrow.